Okay. Welcome everyone to another edition of DGRAV seminar series. For today's meeting, we have Gaurav Chatterjee and Chala from India to present their work on Gaia's black holes and why they are special. Let me introduce Gaurav Chatterjee to begin with. Gaurav Chatterjee is a reader at the Tata Institute of Fundamental Research in Mumbai in the division of astronomy and astrophysics. He works on a diverse set of topics, including exoplanets, planet formation, planetary structures, stellar dynamics, star clusters, and to me, the astrophysics of gravitational waves and compact object binaries, which is very interesting. His most recent work focused on how compact objects, multiple exoplanet systems form. Compact multiple exoplanet systems form, not compact objects, but how dynamical processes can leave potential observable signatures on planetary structures and so on. But today is a special topic on Gaia's black holes. So I invite him to take away and introduce the topic, and his student, Chirag Chala, on his PhD work. Take it away, Chirag.
Am I audible?
Yes.
Okay. Thanks, Satya, for the introduction. It's a pleasure to be with you today. So thanks, APS, for creating this really interesting seminar series. I myself have listened to some of the seminars before. So it's a great pleasure for both Chirag and me to be here. So just to introduce who Chirag is, Chirag Chawla is a final year graduate student. So he has done really nice work about how Gaia can be instrumental in telling us about how high mass stars evolve and form compact objects and their binaries through detection of many such compact object binaries. And he is in the job market, so if you are a potential employer, he will be a great kid to have. So keep an eye out. So today's topic is Gaia's black holes and why they are special. And the plan is I will try to say as little as possible and only give a broad brush overview of why you should care about these things. And then I will let Chirag to take it away and go into the nitty-gritty details. We had to think about a lot of different things to actually predict detection and so on. Okay, so you probably have heard of Gaia. And if you are particularly interested in gravitational waves, then maybe you did not care too much about Gaia because they are not going to detect gravitational waves, but you will see they are going to probably detect a large number of compact objects in configurations that are going to be very useful for us to create better stellar evolution models, especially for high mass stars. And this is what, of course, everyone cares about, and more so the gravitational wave astrophysics community, because we want to understand what we are detecting through the gravitational wave detectors. So before I talk specifically about the Gaia black holes, let's do a quick overview of what we have been doing and how we have been detecting black holes so far. So of course, for a very long time, we have been seeing electromagnetic signals. These could come from as X-ray or radio signals from accreting compact object binary systems. So this is several black holes have been detected this way. Large number of black holes have also been detected through microlensing flyby of compact objects or maybe compact object binaries in front of some background stars, and you see the microlensing event. And of course, we all love gravitational waves, and the ground-based detectors have already detected hundreds of black hole mergers through gravitational waves, right? But you will notice that in all of these cases, so of course, for microlensing, this is a very fortuitous event. This black hole comes in front and it just flies by and never to return and so on. So it's very hard to repeat the experiment, and you cannot get any constraint on the progenitor of the black hole that you have seen. The same can also be true for the black holes that you detect from electromagnetic signals, because you were essentially seeing the accretion disk phenomena. So signal is coming from the inner part of the accretion disk or the jet, and it is not directly telling you much about the progenitor of the black hole that is doing the accretion process. Okay? The same is kind of true for gravitational waves also. So you have, after you detect the gravitational waves, of course, you can put good constraints on the masses and maybe the spins, to a certain extent, the eccentricities. You can put constraints on the redshift of when the merger happened and so on. But without depending very strongly on stellar evolution modeling, it is almost impossible to know much about what star actually created that black hole that we see. Okay. And of course, this is a very interesting constraint to have. So we have, of course, we see all these different types of black holes, and you have all seen these really nice stellar graveyard pictures. So these, of course, the blue are, of course, gravitational black holes detected through gravitational waves. Then these red are black holes detected through electromagnetic signal. And then there are these neutron stars, orange through gravitational waves, and then yellow are from electromagnetic signals. But what you see is slowly and surely the black holes detected through gravitational waves is growing in number. And also you see that the masses of typical black holes detected through gravitational waves are typically more massive than the black holes detected through other channels, okay? So when we have this, of course, this encourages us to learn about how high mass stars evolve and form these black holes, okay? And that, let's say that that is our holy grail, and we want to understand this. And let me just quickly go through what the problems are and what we think may be a solution. Okay. So let's talk about the main challenge. And let me, for now, since gravitational waves, the detection through gravitational waves is becoming so efficient in detecting black holes, let's just simply talk about that as an example case. So let's say that this is time. So at some point, some stars form, right? And then after some time, these stars evolve and form compact objects. And some of these compact objects are in binaries, right? So I have intentionally kept these two at two separate speakers, because whether or not the compact object itself is in a binary system or not, when the compact object formed, there can be a separation depending on the formation channel. For example, if it is coming from formation in isolated binary evolution, then of course when the compact object forms, or both compact objects form, they have to be in a binary. But if you were assembling them through dynamical formation channels, then of course the compact object would form at some time, and then after some time, depending on the details of the kinematic processes that actually assemble the system, you could create the compact object binary at a much later time. And then after some time, the compact binary merges, emitting some gravitational waves. These gravitational waves then propagate and we detect it, right? By the way, sorry, I am recovering from a cold, so I may cough a little bit from time to time. I apologize for this. The way we detect this, we know a lot about this part of the picture. Okay, so compact binary merges, and then we observe the gravitational waves. Okay, but most of the astrophysics, that is the details of part of the astrophysics that that is kind of messy and we do not understand the details of it. That happens in this part. And from gravitational waves, we do not have a model-independent way to put constraints on this. So for example, if you, in the star forms, this part is dependent on the stellar IMF. Then, of course, it could depend on the metallicities, like the metallicity of the molecular cloud may determine exactly how many stars you could form, whether there may be some dependence on the stellar IMF. Maybe there is a dependence on how exactly the slope behaves for high mass stars. So these are all things that, of course, we would like to put constraints on. Then at the time when compact objects form, then of course, before the supernova, what were the properties of the progenitor of the compact object? And that is dependent on the metallicity of the star that will form the compact object. It will depend on the details of the supernova physics, and a lot will depend on the winds because the pre-collapse properties of the progenitor will depend on the winds, and wind then depends on the metallicity. So everything is all interconnected and kind of messy. And then, of course, when the compact binaries, like the compact objects are assembled in binaries, that is dependent on the formation channel. What fraction of the black holes would end up in binary configurations that would merge within a Hubble time, that depends on the details of binary stellar evolution and the environment where you were doing all this assembly. So the point is, there is a lot of astrophysics and detailed modeling that goes on to the side where there is no direct observational constraint if you're observing a gravitational wave event or a population of gravitational wave events. And we have come a long way in improving all these models, although these are very hard, right? So we have very good models. So many groups have worked on this. Some of the work I have done. We know at least qualitatively or so quantitatively, if we assume that we understand the supernova physics and so on. We know what the formation channels are. We can put constraints depending on the various population properties, what is the fraction of different channels and so on. And this model dependent part, it would not have, it should not have bothered you if we knew how high mass stars evolve very well. But that is not the case, okay? So if you look at exactly where our understanding on how high mass stars evolve and form compact objects stands. So there are many different styles of trying to do this or trying to make our understanding better. And this can span a wide range of styles. So you can be like doing prescription-based models and population synthesis, where the focus is to very quickly simulate millions and millions of binaries without paying too much attention on the detailed microphysics of the stellar evolution itself. But this just takes easy to use prescriptions that kind of make sense and explain some part of the observed systems so that we have some confidence in our prescriptions and so on. And then you could also be very detail oriented and go to 2D or 3D hydro simulations. These are extremely expensive, and sometimes these simulations explode, sometimes they do not. There, the idea is to figure out what the mechanism is for the explosion. So basically, the focus is on the detailed microphysics of it. So one thing is for sure is that this is hard thing to do, and we have not solved yet how exactly coming from a zero-age main sequence high mass star, you go and get some population of black holes. So this map is not very clear, and it depends on a lot of messy astrophysics. So the point is, the detailed stellar evolution and supernova simulations are expensive, and even if you could do all these detailed simulations, you need to do observational validations. And that's where one of the problems lie. So we are talking about high mass stars. High mass stars are few, they live very short duration. So we do not have the luxury of having a very large number of high mass stars or a large number of black holes that we can observe and tune our prescriptions or parameters or models. So in general, a model-independent map that could connect your compact object, you could be interested in black holes, white dwarfs, neutron stars, whatever. But a model independent, that should be an underline map that can connect the compact object and the progenitors, that is highly coveted. And we do not have easy means to achieve this. And I think the Gaia black holes or the compact objects that Gaia have been detecting already, and we predicted that it would, that over time will change this statement. Okay, so this is highly coveted, and Gaia will provide this. So high mass stellar evolution is interesting, and very few black holes are detected. And as I have already told you, that through electromagnetic signals, gravitational waves, or microlensing, although we have detected black holes, it's not easy to put constraints on the progenitors of these black holes. Okay. Now, how is this going to change in case of Gaia? Okay. So first of all, binary stellar evolution modeling and population synthesis predicts that if you evolve a large population of high mass stellar binaries, then most of these, when at least one of them becoming black holes, most of these black hole binaries that you end up creating will have luminous companions in very wide orbits. Okay, so most of the black hole binaries are not black hole binaries that would merge within a Hubble time and be detected through gravitational waves. Most of the systems are not going to emit electromagnetic signal because there is no accretion going on. They are wide and they are not compact binaries, so they will not merge. So they will just be a black hole and a luminous companion in a wide orbit, and that's it. But the nice thing is these black holes in these wide orbits could be detected by resolving the orbital motion of the luminous companion. And this was predicted back in 2017. We did this prediction. Martian and Loeb, the same year, came out with the prediction. And Chirag has done a lot of work to improve the astrophysics of these studies and the observational aspects and the biases of the observations he has taken into account and has updated this thing. And what Chirag has found that in many cases, Gaia's astrometry alone could also provide sufficiently accurate mass measurements of these black holes. Okay, so I will let Chirag to talk a lot about it, but I will just broadly tell you about the idea and why these are special. So imagine that you have a black hole that you do not see, and you have this luminous companion that's just going around this black hole. And Gaia, of course, is looking at it without the knowledge of the black hole, and it will detect its parallax, it will detect its proper motion, and on top of that, it will, if the binary orbit is wide enough in projection, it will also detect on top of parallax and proper motion the orbital motion of this luminous star. And this can be resolved by Gaia, and then these can be flagged as a candidate, right? Now, let's say that we have detected some of these systems, and then why is it special? So let's say that you have detected a candidate. It's special because of the following reason. So Gaia provides the magnitudes in 3 bands. So this is G, BP, and RP. So G is a very broadband thing that Gaia is giving for all stars. BP and RP also for all stars. BP and RP are basically the bluish part and reddish part. So for each of these stars, you could, in principle, create a color magnitude value. Okay. Now, from Gaia's parallax itself, you can know the star's distance, and you know the proper motion. And you can find the astrometric solution for the star's orbital motion if the orbit can be resolved. And then, since you know the star's distance and its 3 colors, you can really pinpoint through stellar evolution modeling for these stars. So these stars are basically just sitting outside. They're doing nothing, right? It's just simply orbiting the black hole. So you can very easily put constraints on the mass, age, and metallicity of this luminous companion. And now this is a binary, right? So if you know the properties of the luminous companion, like age and metallicity, whatever has created this black hole, that must have had the same metallicity and age, right? So directly, without depending on any modeling, well, the modeling connecting the black hole to some stellar evolution modeling to connect black holes to their progenitors, just through observation of the luminous companion, you can put constraints on the metallicity and age of the progenitor of the black hole. And then these black hole detections can put age and metallicity can be constraints, and the mass of the black holes can also be constrained because you have the orbit and you have constraints on the mass of the star. And sometimes the errors can be large if you are only depending on astrometry, but a lot of cases, the error bars are small enough that the candidate will be clearly black holes. So basically, the mass estimate minus the error in the mass estimate is significantly above, say, 3 solar mass. So this is definitely a black hole candidate. And since you know the distance, the orbital period, etc., these are very easy targets for follow-up radial velocity surveys. And as Chirag will show, that in several cases, Gaia's low resolution radial velocity, so that Gaia will provide for the slightly brighter stars, not for all stars, that is sufficient enough to give also radial velocity mass constraints. And so that's basically what all I wanted to say. And then I will ask Chirag to just take it away and talk about the details of what our modeling is showing.
Thank you very much. I think if you can hold off the questions until Chirag presents, that would be great. Chirag, why don't you start?
Can you see my screen?
Yes, yes.
Yeah.
Yeah, please go ahead.
Yeah. Is it visible?
Yes, there's no animation, but we can see your slide.
My slides are not working.
I think you have to click on the slide and then maybe.
Let me share it again.
Chirag, try sharing the whole desktop.
Okay.
Only sharing the Keynote app was not working for me.
Okay. Can you see my screen?
Yeah.
Okay.
Yeah.
Now it's
Everything is working. Yes.
Yeah. So Saurav has already told us about how Gaia will be looking at the motion of this luminous companion going around black hole. And from the inferred properties of the luminous stars, such as luminosity and parallax and color, we can infer the mass of the luminous star. And by astrometric fitting of these luminous companion orbit around the black hole, we can have a astrometric mass function. And from the known orbital period and eccentricity and the inferred luminous companion mass, we can have constraint on the black hole, on the dark companion. And if the mass comes out to be greater than 3 solar mass, we can say it's a black hole. So basically, for detecting these dormant black hole candidates, we have 3 methods. First of which is astrometry, which is just based on the idea that due to the presence of the black hole in the binary with the luminous companion will show an astrometric wobble. And if Gaia can resolve its astrometric orbit, then with the inferred mass function and the known orbital period and eccentricity, as well as the inferred mass of the luminous companion, we can have a strong mass measurement constraint on the dark companion. And if the mass measurement comes out to be greater than 3 solar mass, then it's a black hole. Secondly, we have photometry. Due to the presence of this black hole, as you can see in the animation, there is a strong tidal force. and there is a tidal deformation of the luminous star, as you can see in the animation, it will be along the line connecting the two entities. And when the star goes around the black hole, we will have the sky projected angular sky projected area of the star will change, which will automatically result into a time varying flux, which will give us a light signal. And by fitting this light signal, we can have a mass measurement constraint on the dark companion. Third and the last is spectroscopy. As due to the motion of this luminous star around the black hole, due to effects like Doppler shift and time dilation, we will see the shift in the spectra of the luminous star. And again, with the help of spectroscopic mass function, we can have mass measurement constraint on the central black hole. And if again the mass comes out to be greater than 3 solar mass, then we can say the entity is a black hole. So for this study, we have used a binary population synthesis suite, Cosmic, in order to simulate realistic compact binary population. It uses SSC BSC framework to evolve zero-age main sequence binaries from their birth to the present day. For this study, we have incorporated all the relevant binary interaction physics, such as mass loss through winds, mass transfer through Roshlov overflow, common envelope evolution, as well as tidal evolution for during the course of the evolution of these binaries. So how exactly does Cosmic generates the present day BHLC population? So for each of these binary component, we sample the stellar and binary properties such as the masses, metallicity, and eccentricity and orbital period. Likewise, we create our initial binary population, which goes through the intricate binary evolution process, ending up with a black hole and a dormant object, or a dormant companion, which is a luminous companion. And on the right panel, you can see the evolved binary population, where one component of the binary shown in the black dot represents a black hole, whereas the colored component is a luminous star, maybe a main sequence or a post-main sequence companion. One of the most important thing for these binary population study is the choice of the initial binary parameters, which includes primary masses, mass ratio, semi-major axis, eccentricity, and binary fraction, all of which are sampled from various observationally motivated probability distribution function. For this study, we have taken a metallicity-dependent star formation history based on the synthetically modeled Milky Way-like galaxy M12I, which was run as a part of cosmological zoom-in simulation FIRE2. For the supernova engine, which is responsible for the formation of black hole, we use FRIER models, namely rapid and delayed. The difference between rapid and delayed is in delayed, we have a mass gap between 3 to 5 solar masses in the compact object mass function, whereas the delayed supernova produced black holes between 3 to 5 solar masses. For the kicks, we are sampling it from the mixed variant distribution, and for the black hole, we are scaling it down based on the fraction of mass fallback. Now coming on to the result, in the first part, I'll be showing the results of the intrinsic black hole luminous companion population in the Milky Way. So in the first figure, I'm showing you the orbital period distribution of black hole luminous companion binaries. The top panel shows black holes with a main sequence companion, and the bottom panel shows black holes with a post-main sequence. And as you can clearly see, that there is a bimodal distribution, bimodal p orbital distribution, where the outer orange curve shows all the black hole luminous companion binaries. The tighter binaries, which are represented by the blue colors, are predominantly coming from the common envelope evolution. And the wider binaries shown in the in the green curve are coming from the non-common envelope. As you can see, the dashed line shows the first detection cut, which is on the orbital period, which is equals to 10 years based on the Gaia's observational duration. And we can see most of the binaries which will be interested in the, which will be detected in the Gaia catalog will be mostly coming from the common envelope evolution. This is important because from the progenitor mapping, we can understand better the physics of the common envelope. Although Gaia, since you can see the dashed vertical line, Gaia will be sensitive to both binaries coming from common envelope as well as non-common envelope. Now, after this slide, I'll only be talking about the observable, Gaia observable black hole luminous companion binaries in the dormant state. So for the detectability, each binary has to fulfill 3 constraints. First of which is on the orbital period, which we demand to be less than 10 years, because while seeing the motion of the luminous star around the black hole, Gaia should see the motion of the luminous star for all the binaries for at least one full orbit, which would be helpful in accurately fitting the astrometric orbit of the luminous star. Second is on the Gaia G magnitude, which we say that it should be less than 20, because the Gaia position error, which is shown in the third equation by sigma G, get worsened with the fainter Gaia magnitude. And then lastly, we have the sky projected angular size of the luminous companion orbit, which is denoted by the alpha. It should be greater than the Gaia position error. And all the binaries which fulfill all these three constraints, we say that these are resolved by Gaia. Also, we have taken into account a 3D dust map in order to take the effect of interstellar dust and reddening. And also, we have used the metallicity-dependent star formation history, which have the correlation between the position, metallicity, and age of these binaries. So we distribute all these binaries across the Milky Way based on that position, age, and metallicity correlation. Now coming on to the results. In the first figure, I'm showing the cumulative distribution of Gaia-resolved black hole luminous companion binaries as a function of Gaia G. In the orange figure, I'm showing the rapid supernova model, and in the violet figure, I'm showing the delayed supernova prescription. For the astrometric cuts, which are shown in the dashed and the solid line, for the optimistic, which is shown in the solid line, we assume that the sky projected angular size of the luminous companion orbit denoted by alpha to be greater than just the Gaia position error. And if the assumed error is not that accurate, we have the pessimistic cut, where we assume that the sky projected angular size of the luminous companion orbit should be greater than at least thrice the Gaia position error. For the optimistic cut, we find that about 100 in case of delayed and a few hundreds in case of rapid BHLC binaries will be detected by Gaia in its 10-year timeline. And if we talk about the pessimistic cut, we have around tens of black holes coming from delayed to a few hundred in case of rapid. In the next figure, again, I'm showing the Gaia resolved population as a function of Gaia G. But for this time, we are estimating the mass error in the dark companion mass, which is coming from the astrometric observation, as you can see, n in that figure, which is the number of time Gaia would be seeing that binary, and also the assumed error in the luminous companion mass. If the mass of the dark companion, denoted by MBH, subtracted from the error, which is just based on the astrometric observation, comes out to be greater than 3 solar mass, we say that it's a black hole candidate. And as you can see, for 1/3 of these systems, which are Gaia resolved, both in case of rapid and delayed, will have strong mass measurement constraint coming from just astrometry. The other important property of these Gaia black hole is that they show wide range in both metallicity and black hole masses. And also, from the inferred metallicity of the luminous companion, we'll be able to put strong constraint on the metallicity of the black hole progenitor, which is important because it is not possible for the detections coming from X-ray and radio observation as well as from gravitation wave observations. And this will be also helpful in getting a metallicity dependent black hole birth mass function, which again was not possible from the detection coming from the traditional methods. Interestingly, if we plot the detection fraction as a function of black hole mass, we see we do not see a strong correlation between detection fraction as on the black hole mass. Detection fraction here is defined as the Gaia resolved binaries in each of the bin divided by the total number of detached binary in that bin. And since it is flat, we are confident that the observed mass distribution function of these black holes would be very similar to the intrinsic mass distribution of these black holes in the Milky Way galaxy. And if we compare it with the gravitation wave observation, so here the dashed line is the gravitation wave SNR for the LIGO Virgo observation, which is a function of the total mass to the power 5/2. And we see that the gravitation wave observation are biased towards massive black holes, which is not the case for the dormant black holes detectable through Gaia. Till now, I have only talked about these detections just from astrometry. we see that the luminous companion is going around the massive black holes. Hence, we expect larger radial velocity of these luminous companion. And also, for these larger radial velocities, these can also be resolved spectroscopically. So here we also present a follow-up study where for our binaries, we see that about 1/3 of the Gaia resolvable uh, astrometric candidates will also be resolved through spectroscopy through Gaia's own radial velocity spectroscope. And also, these binaries show X-ray counterparts, which is coming from the wind accretion onto the black hole. And from the X-ray observatories like Chandra and Rosetta, we find that about 1/3 of the Gaia result system will also be observed by Chandra and Rosetta, which will improve their candidature. Till now, I have only talked about detecting these dormant black holes through astrometry. From now on, I'll be talking about the detections coming from photometric variability. So the photometric variability signal in such binaries are coming from three important processes. First of which is ellipsoidal variation, which is based on the fact that due to strong tidal force of the black hole, there is a tidal distortion of the luminous star. And when it goes around the black hole, there is a change in the sky projected area of the luminous companion. And hence, due to the change in the sky projected area, we will have a time-dependent flux and a light curve signal. Secondly, due to effects like Doppler effect, time dilation, the emitted flux of the luminous companion will change proportional to the radial velocity, which is the velocity between the observer and the luminous companion. And based on that, we will have a photometric signal. Finally, we have self-lensing, which is similar to the idea of microlensing, but in a binary. Whenever black hole eclipses a luminous star, we see a bump in the magnification and also the flux of the luminous star. And since it's not a microlensing event, we will have a periodic signal. So based on these three signals, we will have a light curve a type signal in such binaries. Coming on to the detectability, the detectability cuts remain the same. We have orbital period less than 10 years, such that each binary is observed for at least one full orbit. And we have Gaia G less than 20 as the photometric precision get worsened with the faint magnitude. And we only study these binaries for which the SNR is greater than 1. In the first plot, I'm showing the reverse cumulative histogram of the Gaia resolved photometrically resolved Gaia uh, photometrically resolved BHLC binaries through Gaia. In the leftmost panel, I'm showing the binaries which would be showing the ellipsoidal variable signal. In the middle part, I'm showing the binaries with the relativistic beaming, and in the final part, I'm showing the self-lensing signal. Comparing the results, in the left panel, I'm showing the results for Gaia. We have thousands of detections coming from relativistic beaming and about thousands of detection coming from ellipsoidal variation, and we have a huge overlap. For this study, we have not only studied the detection through Gaia, we have also studied the number of detections coming through TESS. On one hand, where Gaia would be able to resolve thousands of these binaries. With the help of TESS, we will be able to detect hundreds of these binaries because the test duration is only for 3 years compared to Gaia, which is for 10 years. And also, this study proves that the self-lensing method would not be a good method to detect such black holes because number of black hole detection is significantly less compared to relativistic beaming and ellipsoidal variation. Again, for the photometrically detectable black holes, we again see a spread in both metallicity and black hole masses. And from the inferred metallicity of the luminous companion, it would be relatively easy to constrain the age and metallicity of the black hole progenitor, and hence thus constraining the progenitor properties and also progenitor mapping. Uh, in case of photometry as well, we see not so much strong dependence of detection fraction on the black hole mass. And hence, we can clearly see in the histogram, the gray figure shows the intrinsic distribution of black hole masses in the left for rapid and right for the delayed. And on top of it, the blue curve shows the observed black hole mass distribution. And we see a clear overlap, which was inferred due to the not so much dependence of detection fraction on the black hole mass, which is not for the case of X-ray or gravitation wave black hole detections. Finally, we also see the detection fraction as a function of orbital period, where we compare the photometrically detectable population from Gaia and TESS with the astrometrically detectable population of black holes through Gaia astrometry. And we see there is a sudden rise for the astrometry, which is kind of expected because the more wider the orbit is, the relatively easier it is to detect such binaries. But it is interesting to see the rise in the detection fraction of the photometrically detectable population as a function of p orbital, which tells us that the detection does not only depend on the signal; it also depends on the noise, and the binaries which are present in the larger orbital period have massive luminous companion and hence thus have less noise. And also there is a correlation between the luminous companion mass and the p orbital orbital period, which is coming from the common envelope evolution. As in order to evaporate the envelope, we need a massive luminous companion. So the binaries with the massive luminous companion will end up in the larger orbits. And these two factors kind of explains the rise and fall of the detection fraction as a function of orbital period. Finally, as we have seen in case of Gaia astrometry, that through X-ray and spectroscopic studies, we will have some follow-up observation, which will improve the mass measurement constraint in case of astrometry. Likewise, in case of photometry, we also see that about 15 to 20% of the photometrically detectable BHLC binaries in case of Gaia as well as TESS would also be detectable through Gaia astrometry as well as Gaia spectroscopy. Till now, I have only talked about the theoretical modeling, but with the with the release of the DR3, several observational group have also reported some of these dormant compact object luminous companion candidates, most of which are either neutron stars or white dwarfs, and we have only a few tens of black hole candidates, and the question is why. So in order to have a one-on-one comparison of our theoretical study with that of observation, we expand our catalog of black hole luminous companion by including the neutron star luminous companion as well as white dwarf luminous companion population. In the current figure, you are seeing the cumulative histogram of the black hole luminous companion in red, uh, neutron star luminous companion in violet, and the white dwarf luminous companion in blue. We see that there is an order of magnitude increase when we go from a black hole to neutron stars, and then 2 orders of magnitude in case of white dwarfs. For the DR3 studies, the data is only based on the 3 year of observation. So the orbital period cut on our theoretical estimate is decreased to 3 years. Gaia G remains the same. And finally, we have we have a cut on significance of parallax, which is defined as parallax divided by the error in the parallax, which in the Gaia pipeline should be greater than 20,000 by orbital period. This is introduced in order to remove the false positives. When we include these 3 cuts, we see that our black hole population goes to 0. We have a few neutron stars and about 100,000, about 1,000 white dwarfs.
5
In the
minutes.
current, yeah, okay. I'll just finish. So in the current table, you are seeing in the topmost row that we see that Gaia in its 10-year baseline will have a few hundreds of black hole detection, a few thousands of neutron star detection, and a few 100,000 to a million white dwarf detection. When we introduce the Gaia DR3 cuts, we are left with no black holes, a few tens of neutron stars, and a few thousands of white dwarfs, uh, which kind of meet the observation, which kind of overlaps good with the observational studies till now. So to summarize, from this study, we have found that the potentially detectable dormant black hole will have well-constrained progenitor properties. Most of these detached black holes are not detectable through gravitational waves, X-ray, or radio astronomy. Hence, it creates a complementary set. RV follow-up using Gaia as well as other ground-based telescope can improve the constraint on black hole mass measurement. Some of these black holes also show the X-ray counterpart via wind accretion, which can help constrain stellar wind physics as well as accretion paradigms in binary like these. Coming on to the photometric variability, we see that about a few hundreds to a few thousands of these detached black holes will also be detectable through TESS and Gaia respectively, which is showing ellipsoidal variation and relativistic beaming. And finally, the detection fraction does not strongly depend on black hole mass, and hence the detectable black holes are expected to be very similar in properties to the intrinsic black holes in the detached black hole luminous companion binaries in the Milky Way. Thank you.
Thank you very much, Shaurav and Chirag, for this wonderful work. Very innovative. So congratulations on that. With that, let me open the floor for any questions that people might have. Please raise your hand and I'll call in the order I see. I don't see anything, but let me ask you myself. Let me start. You know, you observe these companion objects. Can you say something about whether it's possible to predict whether the companion will become another compact object or will it be a LUMAS brown dwarf or something? Is that something that you can predict?
Yeah, so since we have mentioned here that the Gaia would be looking at the luminous companion properties such as luminosity, color, and parallax. So we'll have constraint on the luminous companion mass. And from the spectroscopic observation, we can have a constraint on the metallicity and age. So combining these things, we can predict what will the future of the luminous companion.
Yeah, so do you have any numbers? Is that something that you already computed as to how many of them will become compact objects that are potentially detectable after millions of years, hundreds or even giga year, they become observable in the gravitational wave band?
Since most of these binaries are
Chirag,
wider, yeah.
Chirag, do you have the mass of the luminous companion histogram?
Yeah, that's the one that might help.
It's
Because
in
they
the
have to be more than about
I
8 solar
think
mass. Yeah.
it's in the paper. He might have dropped it for time.
So most of these are below 10 solar masses.
Okay.
The
But
observable ones.
right. Is there any reason for that? Is there a selection function that is affecting that you're not able to? So I know for a fact we worked out many years ago with Chris Belchinski. We made a prediction that one of the stellar system, observed binary system, will eventually turn into a binary black hole system. There has been a huge interest whether astronomical observations can determine the number of such binary systems in the galaxy that are still in its either main sequence or post main sequence, whether they will turn into a compact object binary. So you don't have that kind of number here. Is that correct?
I don't have that kind of number here, but since most of these binaries are wide, so most of these would not be merging in the Hubble time.
Yeah, but they have not undergone supernova, and that can turn into whatever binary. It can make the binary more compact, more tight.
Wide.
Yeah.
Yeah. So
Anyway.
if the companion is very high mass, and then it may go to the red giant phase and then create a common envelope and all
Exactly.
that.
Exactly.
And then in principle, it could create a compact object binary. So the paper definitely has a histogram of or the PDF of the mass of the luminous companion for the detectable population.
I will look it up. No worries. Any other questions or comments? Okay, I don't see any other. Thank you very much, guys, for this wonderful seminar, and have a good rest of the week. See you at another meeting. Bye-bye.
Bye. Bye, everyone. Thank you.